Recording is rolling. It is Monday, March 16th. Okay, so back last Thursday, I was out for a jury summons. That's over in Denver, so back with you guys. Okay. But you guys were working on these the cognitive thermo puzzles you guys were working on. I see some of you guys trying to send you guys could work with each other, work in teams. There were these 18 thermo questions that we covered like how to solve in class. Right. So if you turn in today, I'll get that grade as fast as I can. If you haven't turned in yet, then you can turn in next few days, and that'll be one of the first grades on quarter four. Right, so we're going to go into optics. So we'll do some optics this week, right, and then we'll continue optics after spring break. So yeah, we're going to spring break here pretty soon. Right, so today we're going to do reflection ray diagrams. Now, based on how it's gone in the past, it usually takes like most for all in class. Right. Uh, Tomorrow we'll talk about refraction. So you guys know reflection is like mirrors, right? They have some mirrors here, right? Like how does light reflect off a mirror? Right? And then what if the mirror is curvy? So guys, what if you're looking at something like this? You guys have all seen this pig, right? Seen pig, right? Yeah. Now if you get the right angle, it's kind of hard to get this to work on. Oh yeah. Oh okay. It was just working. It's kind of hard to get it to work on the camera. But if I can get just the right angle, you can see this pig pop up right here. See that image? Right? But it's not really there. You can't really think of it. It works really good in person, better than on camera. Right? So if you're in person and you look at it at right angle, right? Right? It has something to do with these mirrors getting curved. They call it parabolic mirrors. Right? So they're not flat. How's that real image created? So we're going to go over that today. Now tomorrow we're going to look at a different aspect called refraction. Right? You guys ever stick a straw in a glass of water? It looks like a straw thing, but broken and bent, but it isn't really. Right? You pull it out, it's actually straight. Okay? Right, or if I take this prism and I move over the letters, okay, ooh, it looks like it shifts them out of place. Right, that's related to something called refraction, and there's a law that can predict exactly how it's going to move, or how the image is going to move. It's called Snell's law. Right? And on Wednesday, I'll get you guys some lasers. I got a whole box of lasers now, and like some curvy prisms and how you guys record. Right? Thursday and Friday, we'll do a zoetrope activity, and there's more optics I want to do, but we're going to save that for after spring break. Right. So you guys good with the agenda so far? Agenda? Right. Right. So let's look at here. I got some demos lined up about things that you'll eventually see this class period. Right? Maybe not in this order. Right. But you guys ever seen in front of a funhouse mirror, like these curvy mirrors? Now these mirrors, some parts they might be convex, like they bow out, and some are concave, like they bow in. Right. And it creates all these weird images, right? But why would they create these images exactly? How would you know which ones are concave and convex, right? And why does a flat mirror create like a pretty perfect looking reflection, right? Oh, how about ooh? Okay, now this is also an example of reflection, but this is more acoustic reflection, but it's the same principles as what you guys are going to see. Okay. Has anybody ever seen these dishes out anywhere? I know if you go to University of Florida, if you go in the physics building, they have a pair of these in the lobby of the physics building. These are called whispering dishes. And it is, if you stand at the focal point of it, I'll show you guys what focal point is here in a few minutes. But if you stand at the focal point of one of these dishes and you whisper something very softly that probably somebody past about 5 feet couldn't hear you at all, okay? It'll actually concentrate the sound reflected across the field. And if somebody else on the other side of the field has their ear on the focal point of the other dish, they'll be able to hear it just like you're whispering right in their ear. So why is that? Why is the sound concentrated and reflect like that? Okay? And there's a natural accidental version of this, which is called a whispering chamber or whispering gallery. A lot of domed buildings have these accidentally built. So again, this guy's whispering, maybe this guy can hear him across the room, which you shouldn't be able to otherwise, except for how the architecture. You can see each one of these rays. Right? So if it was like a straight line shot, hey, everything's being reflected to this guy over here. We're going to create some ray diagrams today, look kind of like those. This often happens in Capitol buildings. Right? You guys know the U.S. Capitol is a dome building, right? It has these domed rooms, and a lot of state capitals also take that plan and say, hey, let's also build these dome buildings for our own legislatures. So or legislative buildings. So if you have two legislators over here whispering to each other, they think nobody can hear them, then there might be, if you know a guy that knows physics or knows where the spot in the room, he can spy on and listen on them. Right, so that's happened. I remember one story, I forget who, but there was a story of one guy who actually put his desk at one of these, so he would just like spy all day, every day on all his colleagues to do that. Okay, so that's going to show up later today, right? Not right away, right? But let's start with a basic reflection, just real basic reflection here.
Consider a candle. All optics books consider candles for objects, okay? Now we're going to look at the image that this candle gives in a mirror. Let's suppose right here, we have a mirror surface. Now what happens is light, let's just take from this point. Light goes in all directions. Some comes straight ahead, some comes up like this, some comes like this. The light hits the mirror in all directions. And when it hits the mirror, it boom, reflects, yeah? And it reflects how? There's a normal, a normal, a normal, a normal. It reflects such that this angle, for example, here, will be equal to this angle here and reflect like that. And up here, this will reflect right back to where it came, yeah? Because it hits flush, huh? Right angle. Huh? Up here, like that. And up here, that, down here, like that. Where this and this are the same. I don't have that drawn very well, huh? Like that. Get the idea?
All right. Here's where he says this angle here, we'll call this the angle of incidence. And this angle here, we're going to call the angle of reflection. The fact that those are always the same, that's called the law of reflection. So if you open up a physics textbook or Google the phrase law of reflection, yeah, that's exactly what he's talking about. Okay? Now, as long as it's a flat plane mirror, this is really pretty straightforward so far. Right? Now, do you guys notice that the angle that he's measuring with respect to is with respect to this normal line, this line that's perpendicular to the plane? So hold on to that idea.
Now, you have your eye out here and you're looking. These rays here are all diverging. They're spreading out. See? They're spreading out this way, just as if they were this way. See? It's like this continue, huh? But that spread out looks to you like that ray came from back here, that ray came from back here, that ray came from back here, that ray came from back here. It looks to you out here like there's a flame here and also a flame back here. And I could draw the same rays for the bottom of the candle. That's done in your book a little bit, yeah? Okay. And the bottom of the candle, it would look to you like it's over there. And so you would see the candle here, and you would see the image of the candle.
All right, so he said optics books use candles. I guess his use candles. A lot of optics books I've seen use arrows. I really don't like arrows myself because there are all these arrows in the rays. Right, I'm going to use stick figures. Right, so I'll have stick figures where he has a candle. Right, right. And I see two candles in his picture, but one's the actual object, so I'll label the stick figure object, and one's actually the reflection, and I'll call it the image. Right, so there's an object and an image.
And let me ask you a question. What's the distance here, and the distance here? Begin with SS. Same, gang. Same.
Right. Well, he says same, but really that's only true for a flat mirror. Right? Right. So if you have a flat plane mirror, which probably most of the mirrors that you care about, right? You're brushing your teeth, looking in the bathroom mirror, you just have a flat plane mirror. Right? This, like if this distance is 1.5 meters, this distance is also 1.5 meters. Right? But if you get one of those curvy mirrors, concave, convex, or funhouse, right? That kind of goes out the window. That's not necessarily the case. Okay? So here, let's bring this over here. All right, so he just told you this right here, law of reflection. Right? So this angle of reflection matches this angle of incidence for any particular ray. I'm just following one ray. There are like a bajillion different rays leaving this candle flame going in a bajillion different directions. Isn't that true also? Okay. But if you just follow one, it bounces off mirror. And notice that we're measuring with respect to this normal line right here. So that's okay so far, right? Okay. All right. And what if you have a curved surface, like a mirror ball? Can you guys imagine like a giant mirror ball? Right? Or how about the backside of the spoon? Can you guys imagine the backside of the spoon? Guys, what does it look like if you look in the backside of the spoon? Well, careful.
It looks.
I think you see, look right side up on the backside of the spoon, right? Like this. Right? You look right side up, and you look really tiny, don't you? Right? I think you'll see that show later. Right? But I need to define how curved is some curved mirror, because we're going to do that in a few minutes. Okay? And how curved is a curved mirror? Well, if you have a certain radius of curvature, you guys see this R for radius. If you divide that by 2, it will tell you this focal length, like this focal distance from the surface, or I guess from the center, because it's over 2 either way. Okay? And what that means is, here, if you follow this light ray, you guys see this light ray I have in red here, maybe it's a laser light. Right? If you aim straight towards the center, of course the light ray is just going to bounce straight back. That's okay, right? Straight there, straight back. Right? But what if you offset it by a few centimeters? And also aim parallel to, well, what if aim right at the center? Right? It's going to bounce off. It's going to reflect this way. And if you extrapolate backwards, that goes to the focal point. Or other way around. If you ever aim a laser straight at the focal point, it'll bounce off the point parallel to as if you had aimed it at the center. Right? So you can think of it that way. Okay. And so when we get to like convex or divergent mirrors, right, we look at that. Alright, so everybody has a paper. Guys, write your name on your paper. We're gonna do this ray diagrams activity. Okay? So we'll call this ray diagrams. Okay, and call it reflection. Reflection. Okay. And next couple days we'll also do refraction. And Snell's Law Lab. I'll give you guys some lasers so you can try it out yourself. Right? But for the reflection, we'll just do these diagrams. Okay. So let's do 2 examples on the side. So example 1 is going to be a plane mirror. Plane mirror. Okay. So probably not a whole lot different from what Paul Hewitt did, but you guys go to try it out with your own hand and your own pencil. Okay. Then we'll do a convex, or you might see it this way, a diverging mirror. Okay. We'll do one of those, and all these are kind of the same. Like we can do 10 different examples, but they aren't like super different from each other. Okay. Okay. And then later on, we'll do 3 examples of concave or converging mirrors, and those will lead to a few different scenarios. Okay. Okay. So you guys good with these so far? You guys got what I got on your paper? Okay. You wrote your name, you wrote ray diagrams, reflection, so that when I eventually score this and hand it back to you, or put it back in your return folder, you'll know what you're looking at. Okay, it's not the refraction, it's the reflection. We're talking about mirrors. We're talking about mirrors here. Mirrors. That's what reflection is, mirrors. Okay. All right. Now, for a plane mirror, draw draw a ground line. So here's the ground. I'll label it ground. Well, I'm gonna label all these ground, but at least that one. Okay. All right. And let's have a mirror. And this is a flat plane mirror. That's what plane is, right? Flat. So this is flat. Okay. And on one side, draw a stick figure. Maybe put his feet on the ground here. Feet on the ground. Okay. And I'm going to label this guy object. Okay. Because he's in the real world. He actually exists. Okay. But he's looking in this flat plane mirror, and he's seeing this reflection. And the question is going to be, where does this reflection show up? Where does it look like it would be according to him? Okay. Now, of course, you guys know the answer to this question, because every time you brush your teeth every day, you're looking at a flat plane mirror. And guys, if you're standing 1.5 meters away from the mirror, how far away does your reflection appear to be on the other side? 1.5 meters on the other side, doesn't it? Right. So you know what the answer is going to be, but let's go through this procedure. And then later on, when I change the mirror, we'll use the same rule, but we'll get a different outcome. Okay. Okay. So Paul Hewitt had, I think like 5 different rays bouncing around. You can actually get this with just a couple of rays. Okay. So we're always going to go from the top of his head. Right, we're going to bounce 2 rays, and then I'll show you how it's all. That's right. Okay. So 1 ray, let's bounce straight at the mirror. Straight to there. Okay. Now, guys, since it's a flat plane mirror, is it just going to bounce straight back? Okay. And when it bounces straight back, and he sees it bounce straight back, you can extrapolate to the other side. You say, well, it looks like it came from like this direction. Did it? Like that. Okay. So his reflection is going to look like somewhere over there. Okay. Right. What if he wants to look down his feet? Oh, okay. I'm realizing as I'm going through this, you guys are my only honors class, and the only class I'm doing this, but I realize in the past I've actually done some of these curving ones first, and I realize why that's okay. Okay. We'll go with this. Okay. What if he wants to look down at his feet? Can you guys guess where he has to look at this plane mirror so that you can see the reflection of his feet? Yeah, probably about halfway down, you guys think, right? Okay. Because if he looks halfway down, couldn't this bounce in such a way going where it bounces back to his feet that way? Would that be true? Okay. Okay. So, or you could go backwards. If there's a light ray that leaves his foot here, it could bounce off the mirror, and because of law of reflection, this angle of incidence matches this angle of reflection, theta I, theta R, and with that could go up to, well, his eyeballs are close to the top of his head. You guys get the idea, right? Yeah. Okay. And what does he see then? Well, from his perspective, it looks like this ray came from this direction. You could keep going. I don't know if I got that exactly right. I missed it a little bit. That's all right. Just get the idea. Back from that direction, like that way. Yeah. And by a little too high. I'm going to mess this up a little bit. Let me try to correct this a little bit. Looks like it came back from kind of that way. Okay. So he perceives his foot as being in that direction. Okay. Now, you could add more and more and more rays. Probably would have a few more than I did. Okay. It looks like his feet are going to be here. He perceives his head being here. Right? You can draw the rest of the image there. And this would be the image. That's kind of result. Okay. And then if you wanted to measure these distances, what's the distance from the object to the mirror and the distance from the image to the mirror? Okay. I'll call this D sub O for distance object and D sub I for distance image. All right. Now hold on to that because yeah, I really should have done some of these curvy ones first, but we'll come back to that and I'll show you guys. This is going to line up in a certain equation. I'll show you guys the equation in a few minutes. Okay. Let's do a convex mirror or a diverging mirror. Okay. All right. So convex diverging mirror. Okay. Now let's get another ground line going. All right. So here's the ground. Draw the object, which is the actual guy here. Okay. Now this time, let's draw a curvy mirror, like looking in the backside of a spoon. Okay. I'll make this kind of big just to exaggerate a little bit. Yeah, but this guy's definitely looking in the backside of the spoon, isn't he? This object over here. Okay. Right, he's looking at the backside of the spoon. Okay. So what do you see looking at the backside of the spoon? Well, you guys probably know you see a version of yourself that's upright but really, really tiny, right? Really, really tiny. Okay. So that should be what we get. Okay. Now I need to define how curved is this. Like my flat mirror wasn't curved at all, but the spoon is. Okay. So that's going to go back to this. I guess if I turn this upside down or matches my picture, doesn't it? Okay. So I need to put a focal point somewhere to define how curved it is. And you guys know, of course, there's this relationship. Tell you something about the radius of curvature. So I'm going to throw a focal point. How about right here, just to throw a point? It doesn't matter exactly where you put it. Just get the idea. It's a little bit abstraction. Right? Now, of course, if you had an actual spoon in front of you, there'd be some number of centimeters. This would be, wouldn't it? Okay. Right. Right. Okay. Right. Now, how are the light rays going to bounce here? Right. Well, let's go top of his head, parallel to the ground. I mean, we had one of those before, parallel to the ground. It just bounced straight back before on the plane mirror, but that's not going to be true on this one. All right. All right. You guys ready for this? Okay. Any ray that travels parallel to the ground here is going to bounce off in such a way that the light ray would line up exactly with the focal point. Remember, that's how you find a focal point. That's what the focal point is. Okay. Okay. So this light ray sort of extrapolates backwards this way. So yeah, go ahead and dash that. Okay. Because if you were in the real world on the side of the sky with the object, maybe you are the sky and your eyeballs are looking this way. Okay. You perceive there being a ray that comes this direction. Okay. Okay. Of course, no light actually crosses the mirrored surface, but if you're over here, it sure looks like it does, doesn't it? It looks like there's something out on the side. Okay. Now let's take another ray, and we're going to aim straight for the focal point. Aim straight for the focal point. We'll start at the top of the set again. We'll aim straight for the focal point. Okay. Now, of course, you guys know no light's actually going across the plane. Okay, but so I'm going to dash. Anything at dash, no light actually goes that way. Okay. It's just going in that direction. Okay. When it hits the surface and reflects, guess which way it's going to reflect? Back parallel to the ground is what it does. Back parallel to the ground. Okay. Which means in the real world, right, inside the object, you think this light came this way. So I'm going to dash, 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 extrapolate backwards where it looks like it came from. You see that? Okay. So here, verbally repeat that whole process we did. Right? Because what we did, we're going to repeat that process over and over. For different kinds of mirrors, we'll get different kinds of results. Okay? So we'll start at the guy's head. We're going to aim straight for the mirror parallel to the ground. That's always going to reflect off the wing so that the light can extrapolate backwards through the focal point. Okay. Again, if you want angle of incidence, angle of reflection, here's your angle of incidence, here's your angle of reflection. They're the same angle, right? Yada yada. Okay. Okay. And then we're going to go from top of the head straight toward the focal point. And that's going to bounce off in such a way. Yeah, law of reflection. Here's your angle of incidence. Here's the angle of reflection that are different than that other pair. Okay. Bounces off parallel to the ground. Right. Of course, you can go vice versa. If you had a laser light parallel to the ground this way, it would bounce off so it extrapolates back to the focal point. It's kind of are you guys good with that process? You guys get that? Okay. Now, again, you could repeat the whole process for his feet, but since his feet are on the ground and I have the focal point also on the ground, it's going to be no different than the plane mirror itself. So his feet are always gonna show up on the ground, even in the reflection. Just how we're doing this. I'm always putting his feet on the ground. Okay. Now, do you guys see where these lines cross right here? These dash lines? Do you see that? They cross? Okay. That is where his image is gonna go. So put the top of his head where those lines cross. We're gonna put his feet on the ground. And there's your image. Image right there. Okay. All right. Yeah, hey, it's not consistent with. If you look in the backside of the spoon, you see a upside, right side of the image of yourself. That looks really tiny. That's exactly it, isn't it? That's exactly it. Okay? If you look in a mirror ball, suppose you have like a spherical mirror, maybe a really shiny bowling ball. Yeah, I bet you see something like that, really tiny version of yourself, don't you? Yeah. Next time you see something like that, your convex mirrored surface. Okay. All right. Well, I want to break out an equation at some point. So okay. Everything we just did, got a poster for. Looks like this, right? And this image location you can actually determine with this map. So it says, so DI is distance of the image from the mirror, DO is distance object from the mirror, and F, well, this context, it's the distance to the focal length, right? So the distance from the focal point to the mirrored surface, right? So let's try this out. And since we have some diagrams, let's start with the one we just did. Okay. I'm going to actually measure with my ruler. We'll see how close. That formula should be fairly close. Might not be 100% exact, but should be pretty close. So I'm going to try this out. So distance object I have right here looks like 5 centimeters. Pretty much on the nose, 5 centimeters. So I'll call it VO equals 5 centimeters. Right, guys, yeah. Okay. Now, how about my focal point? What's my focal length, I should say? If I go from the mirrored surface to this focal length, it looks about 6 point, I'll call it 6.4 maybe. Okay. So this focal distance right here, I'll call F equals 6.4 centimeters. Okay, you guys get it? Got that? I got that? Okay. Now, if that's all I gave you, and told you it was convex, you should be able to mathematically predict what this distance image is. And it looks like maybe a little shy of 3 centimeters, a little bit less than 3 centimeters. Okay. So let's try that formula right here. And what I just showed you is 1 over the focal length is 1 over distance object plus 1 over distance image. Ooh. That would be a good formula to have you guys calculate on a quiz. It would have to be after spring break. There's not going to be any more quizzes before spring break. Right? Right. But let's throw all these numbers. Let's say I want to calculate this distance image right here. Let's do that. So I'll do 1 over F, which is 1 over 6.4. You guys know these are centimeters. Centimeters. Okay. Equals 1 over distance object. 5 cent. Oh, whoops. I gotta do one more thing. Guys, if you're in front of the mirror, let's call that positive. And if you're behind the mirror, let's call that negative. Is that okay? Okay. Because that could also help define, is it a convex or concave mirror? That would make a difference too. So guys, I'm going to change to 6.4. Because what I'm going to change to 6.4 to? Negative. Yeah, negative 6.4. Is that okay? Because the focal is on the opposite side. Okay? Okay. And then I'll say plus 1 over distance image. Okay. And we're going to solve for distance image. Okay. Now it's a little cramped space right there. But in the calculator, I'll do 1 over negative 6.4. Right. Guys, can you do the algebra with me? Can you subtract over 1 over 5? Is that okay? They say minus 1 over 5. Is that okay? Okay. Now this is equal to 1 over di. So if I want di, distance image right here, what's the last step I have to do? Take the what? Reciprocal? Can I do reciprocal? 1 over like that? Okay. And it's telling me negative 2.8 in centimeters. Okay. So according to the map, the image should show up 2.8 centimeters on the opposite side of the mirror. Okay. Well, it definitely shows up on the opposite side, so definitely negative. That's consistent with the negative. Is that true? Okay. Well, what did I get again? Didn't I say a little shy of 3 centimeters? It sure is. Look at that. Okay. I wasn't sure if that was going to work out 100% well, but that's pretty dang on the nose, isn't it? 2.8 centimeters on the other side. You guys see that? Okay. You guys see how these ray diagrams in this map tell the same story from different perspectives. Right? They'll give you the same answer. Okay? Is that right? Well, guys, if that's true, let's go back up and check this plane mirror. Let's run the same equation, but we'll put in the numbers for the plane mirror. Okay. So I can do 1 over focal distance is 1 over distance object plus 1 over distance image. Okay. So probably straight from the poster or textbook, whatever. Okay. Okay. Now, guys, the trick part here, if you can figure out the answer to the next question, everything else is going to fall in place. Okay. What do you think is the focal length for a plane mirror?
0.
It's the opposite of 0. Infinity? Yeah, that's about right. Right? Because imagine you have a let's look at this picture right here. Right? There's some focal length. If I make the plane mirror flatter, or sorry, make this mirror flatter and flatter, the focal point moves further and further away. Okay? And if I have a spoon that's not curved at all, it's like a little spatula or something. Yeah. The focal point has moved infinitely far away. So in place of this F, I'm gonna put infinity. Guys, what is 1 over infinity? Zero. Right. And then here, let me get a measurement here. So this object was about 5.5 centimeters, 5.5 centimeters. Right. And we'll say plus 1 over di. Let's say I'm solving for di. Right. Now you know this right here is 0, so I'll put 0 right here. Equals 1 over 5.5 centimeters plus. Right. Now you could do the algebra and finish this out. Or you could look at this by symmetry and you could realize already what this has to be to zero out. Because there's only one number here to zero out this equation. What is that? Negative 5.5. So distance image is negative 5.5 centimeters. All right, you guys see that? Negative 5.5? Okay. So according to the math, the image should show up 5.5 centimeters on the other side. And it definitely does. Aha. Okay. Right, okay? Okay. So recap what we've done so far. Okay. Okay. Here's the poster version of what you guys have. Right. Oh yeah, I did swap those. Oops, sorry, I should have done this one first. That's okay. You have it all anyway. Okay. But you can do these ray diagrams. You can follow as many rays as you want, but really you can just follow a couple of rays to figure out where is the image going to be using the ray diagram. Right. This focal point tells you something about this focal length. Tells you something about how tightly the mirror is curved. Okay. And this equation will predict exactly where the image is going to be. Or I guess if you know any two of these, you could solve for the third, right? Wouldn't that be true? Right? Is that okay? Yeah. Yeah. Guys, I'm making a recording right now. I'll post it later. Okay. Yeah, I'll post it. All right, you guys got all that? Okay. All right. Now, are you guys ready to flip over and do concave? You guys ready for concave? All right. So you can flip your paper over. Let's go over. Okay. And we're still doing reflection, but let's do concave mirrors. Concave mirrors. Concave. Okay. Right, so for this case, let's see what I want to do here. Okay. Let's get 3 mirrors. Okay, so put one line straight across the middle of the page, one line about a quarter of the way up, and one line about a quarter of the way down. Okay. Can you guys get 3 ground lines like that? Right, so we're going to do 3 examples: mirror, mirror, mirror. Okay. And if the last example was convex and it was looking in the back side of the spoon, is this going to be opening like a cave, like you're looking at the front side of the spoon? Do you guys think? Front side of the spoon? So go ahead and draw mirror, mirror, mirror. Okay, 3 concave mirrors. You guys got 3 concave mirrors going? Okay. It might be a little of a tight fit. They might overlap. But that's okay. Right, you guys will distinguish. Okay. Okay. Got it. You guys got 3 mirrors. All right. So now we're going to be looking at the front side of the spoon. Okay. Now we need to define how tightly curved are these mirrors, right? How tightly curved? Okay. So let's make sure I get a good example for you guys. Okay. Let's make it all the same. Let's try this. Put a focal point right about here for all these. I'll call this focal point, focal point, focal point. Okay. We can use the same equation as we did before. So you can predict with an equation. Looks like I put about 5.5 centimeters on pretty much all 3 of these. Yeah, right. All 3 of these are pretty much 5.5 centimeters away. Okay. Okay. What I am going to change is where the object is located. So on the first one, let's put the object inside the focal length. Label this guy object. Oops, I need to put his feet exactly on the ground. That'll help. Okay. The second one, let's put him outside the focal distance. Let me see. Put him. Where should I put him exactly? Okay. How about back here? Okay, object. Okay. Because if you slide him around like too much in one direction, it's kind of hard to fit all the lines on the paper. Right. Okay. And the third one, let's put him right on top of the focal point. See what happens. Okay. So there's object, object, object. Okay. You guys got all that? Okay. Now. Okay. Everybody got what I got so far? Everybody's drawing all that? Right. Now, what you'll notice too is what we're setting up are really situations for these mirrors too, isn't it? Right. Like this right here is a concave mirror. So if you can hold this close to your face or far away, I don't know if it works like so well with the camera, but here, I can pass around these two halves. I mean, they're both concave mirrors. You can try this out yourself. You can do a little experiment. And you should see what we're about to be finding out in the next few minutes. Okay? About to see? All right. And here, just for to give you guys a little better visual of this. Here, I do have a video of this too. Okay, so that pig right there is actually not actually there. It's just a reflection, right? Okay. Oh, I meant to mention too. Anytime it looks like the image is hovering in front of the mirror, like it does here, and like if you put those two halves back together, then they'll say that too. That's it's called a real image. Okay, like a real image, as opposed to a virtual image. Like if you're brushing your teeth in front of a plane mirror, and it looks like your reflection's on the opposite side. Okay, there's the actual plastic pig, and there's the illusion, right? Okay, right, okay. So I can do that too. If I flip back to what we had before, remember I was calling this guy's image, right? I can modify it a little bit. I can call this virtual image, virtual image. That's what we did a few minutes ago because it looks like it's on the opposite side, right? But that won't be the case necessarily for all of these. One of these might be a real image, but we're going to find out which one. Right, you guys ready? Okay. So let's start with if you're inside the focal length, inside that focal distance. So let's take one line, run it parallel to the top of its head. So if there's a laser light, it shines that way. Okay. Guys, which way? See if you guys can figure this out. You might be able to figure it out by now. Which way is this laser light going to bounce? Straight through the focal point. Okay. So do you guys have those two lines also? Okay. So you got this ray light right in the top of his head, parallel to the ground. That's got a boing, go right through that focal point. Okay?
How do we know where it is on the mirror? Is this supposed to look
Okay.
through his nose?
Okay, guys, here, I'll say it again. Guys, the very first line, hold your ruler parallel to the ground. You guys hold your ruler parallel to the ground. Okay, and go skirt right across the top of his head. Okay? Okay, go right across the top of his head, parallel to the ground. Okay? Now, if that was a flat mirror, like a plane mirror, wouldn't it just bounce straight back? Okay, but this is a concave mirror, so it's going to bounce down to the left. Where down to the left? Well, that's where we lay down a focal point, and that will define exactly where the ray crosses. Right? Like that. Right. Now, we still need another set of rays. Right? This is not the answer yet. Okay. But guys, do this. That last ray you just drew through the focal point, extrapolate backwards behind the mirror. Doesn't it look like the ray came from that direction? Is that true? Even though, of course, no light actually crosses the mirror, but you guys know that. Right? But it looks like it came from that way. Can you guys extrapolate backwards a bit? Let's do that. Okay, everybody got that? Okay. Now, let's have another ray go from the focal point across through the top of his head. Okay. So we're starting at the focal point. Everybody start at the focal point. Go through the top of his head. Skirt the top of his head right there. And guess which way that's going to bounce off? Parallel to the ground. Back parallel to the ground. And also parallel to the first ray, which was parallel to the ground. It's all parallel. Okay. Now, before you move your ruler, which way does it look like that ray light came from? Back behind the mirror, doesn't it? Doesn't it look like it came from this way? True?
Yep.
Right? Here, we'll repeat everything I just said. Let's go back in time a little bit. Okay, so the first line you do was skirt the top of his head parallel to the ground. That bounced off the mirror, boing, straight through the focal point. Or you could, of course, vice versa, go backwards, boing. Okay. Then let's start at the focal point, skirt the top of his head. That's going to bounce off the boing, parallel. Right? Anything that goes through the focal point has to bounce off the mirror parallel to the ground. And that's how we sort of define the focal point in the first place. Okay? Okay? And every time these lines are bouncing to anybody in the real world, like this object, it looks like those lines came from behind the mirror. So go ahead and extrapolate backwards. Okay? Do you guys see where those two lines cross? Guess what's right at the point where they cross?
Right.
Starts with an I. Image. Yeah, so no light actually does that. And would you call this a virtual image also? Because that's like it's on the opposite side. We'll call this a virtual image. Okay? While you're finishing, write that down. I might have enough space over here to do the math. Let me see if I can do the math over here. So 1 over the focal length is 1 over distance object plus 1 over distance image. Okay. Let me do the same as I did before. Let's say calculate. I want to calculate where's the image going to be. Now let's see how close it is here. Okay, so 1 over 5.5. You guys know these are all centimeters, right? Okay, equals 1 over. Now where's my object? Okay. Object is looks like about I'm gonna say 2.4 maybe 2.4 centimeters plus 1 over distance image. Right. And these are both positive. Okay. Guys, shouldn't these both be positive because they're both on the front side of the mirror? The positive, right? But for DI, should I get a positive or a negative number? Negative, because it looks like the image is on the other side. Okay. So here, I'm gonna do some algebra in my calculator right here. I'm gonna go 1 over 5.5. What's the next thing I should type? Minus 1 over 2.4. Is that true? Because I'm subtracting this over. Is that okay? Okay. And now that's 1 over DI. So what do I have to get DI? Take the what? Reciprocal, like 1 over the answer. Is that true? Okay. And it says it should be negative. Yeah, it's negative 4.2 something centimeters. Right. Okay. Yeah. So it looks like my ray diagram missed it a little bit because here I'm looking at about maybe 2.5 centimeters. So it's not 100% there, but it's pretty close. Pretty close. And it is negative. It had to be negative. Okay. So it's pretty close. It's close enough. I'm happy with it. All right. You guys get that? Right. Right. So here's the math. Here's the ray diagram. They're both telling approximately the same story. Okay. Okay. Oh, did you guys see that too? When I passed around those mirror halves, if you hold your face really close to it, it just did it blow up your face? Yeah. Right. And if you have one of these mirrors, now on this side it's a flat plane mirror, but if I flip this over, right, it has a little bit of concavity to it. Hey, you guys ever use one of these cosmetic mirrors? Right? And isn't the purpose of a cosmetic mirror to blow up your face? It does. Right now you look bigger. That's exactly right. But what if you take this mirror and you hold it too far away? Hold it really far away, or those mirror halves that I passed around. What's that going to look like? Well, let's run through that. Right, you guys ready? Right. We're going to do the same procedure. So let's go parallel to the ground. Okay. Ooh, guys, we got about 7 minutes, so I'm going to try to pace this out correctly. Okay. You guys, which way is that ray going to bounce? Through the focal point. Boing, through the focal point. Now, before you move your ruler, can you play backwards? Boing, 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 boing. Go backwards. Is that okay? Oh, actually, you know what? That's not necessary for this one. I forgot. Okay, don't worry about that. Okay. Definitely do that. Can you guys go boing? Can everybody just go boing? All right. Now, let's go from the top of his head through the focal point all the way to the mirror surface. And which way does that ray bounce off? Parallel to the ground. Boing. Gonna go that way. Yeah, I did. Okay. I should have backed this guy up further. That's okay. Let's look at the end. Alright. You guys see where there's two lines cross? 2 lines cross right there? Here's that. That's the top of his head and the reflection. And furthermore, he's gonna be upside down because his feet are always gonna be on the ground line because the ground line also goes through the focal point. Is that too? Right. So here's the image. In fact, it's not just any kind of image. Guys, this is the first one we've done where the image shows up in front of the mirror. That's not a virtual image. That's called does anybody know? It's called a real image. Okay. Which is exactly what you saw with that pink plastic pig. Didn't it look like it was hovering in front of the mirror? Is that true? Okay, you guys good there? Okay. Okay. Now, you know what? If I had another shot at this, I should have put this object further away. And I'll tell you guys why. Because if you put it further away, then the image actually shows up where he can see it. Right, so, which is more fun, but okay, right. So we basically did this and this, though, didn't we? We just did that. We just did that. Right. Right. And what you might be thinking is, hang on, we got those 2 mirror halves passed around. You guys can try this yourself. If you hold your face close to the mirror, you see a large version of yourself upright. If you hold it too far away, you're going to flip upside down. You guys try that too. You guys hold the mirror really far away and it flips you upside down. Right. But what's halfway between this and this? What if your eye is right on top of the focal point? Right on top of the focal point. You guys get that? What did you see? What did you see if your eye was right on top of the focal point? And it wasn't this and it wasn't this. What's halfway between this and this?
Something else.
Yeah, it's like something else entirely. Because these are like categorically different, aren't they? Well, let's find out. So, investigation. Right, so, same process we did for the last few. All right, the script top of his head. Just go focal point, straight to the focal point, which is also where he's standing. Right, is that clear like that? Okay, everybody just go to the point. Okay, and then let's go top of his head. Through what? Through the focal point. Oh no, that's a vertical line. Because he's right on top of the focal point. Is that even going to cross the mirror? No. No. So our process that worked for the last border diagram kind of falls apart. Huh. Which means what how could you interpret this?
He's invisible.
No image. Right. So guys, those concave mirrors that are being passed around, right? If you back it up, you'll see this. If you put it close to your face, you'll see this. And if you get it right in the middle where your eyes are right on top of the focal point, you'll see a blur of light where there's no discernible image at all. Okay? Hey, guys, that? Yeah. And of course, you could run the math on all these too. Great. Here, guys, since we got 3 minutes of class left, go ahead and finish anything you need to finish, and then turn that into the grade tray. I'll give you guys points for that. That'll be one of the first grades this semester, right? Along with that thermo packet. I see a lot of you guys already turned in the thermo packet. If you haven't turned that in yet, you can turn that in tomorrow too. Okay, so tomorrow we'll talk about refraction and Snell's law, and then Wednesday I'll have a lab for you guys, and we'll be getting closer to spring break.